In 1935, a farm tractor had 1,200 critical parts. Today, a Boeing 747 has 4.5 million. That's not progress, that's a ticking time bomb. Because with every added component, the probability of catastrophic failure doesn't just increase, it multiplies. This is why reliability engineering isn't optional anymore, it's survival. Welcome to academic engineering. We explain what textbooks assume you already know. Today you're learning why reliability became the most critical engineering discipline of the modern era. Not because it's interesting, because ignoring it ends careers, destroys companies, and costs lives. By the end of this video, you'll understand the forces that made reliability non-negotiable, the formal framework every engineer must master, and why your professional responsibility goes far beyond making things work. Here's what changed. 50 years ago, if your product failed, you lost a customer. Today, you lose everything. Four forces converge to put reliability at the center of engineering design. First, market competition. Your competitor's product works 99.9% of the time. Yours works 99.5%. You're out of business. The margin for error disappeared when global markets gave customers infinite alternatives. Second, financial stakes. Modern engineering systems cost millions. A single commercial aircraft, $200 million. A telecommunications satellite, $300 million. When acquisition costs reach these levels, failure isn't inconvenient, it's catastrophic. Third, public pressure and legal consequences. Engineers used to operate in obscurity. Now, every failure is documented, publicized, litigated. One well-publicized system failure can destroy decades of reputation and trigger lawsuits that bankrupt companies. Fourth, complexity explosion. And this is where it gets critical. Let's talk numbers. 1935 farm tractor, 1,200 critical parts. By 1990, that same tractor, 2,900 parts. That's a 240% increase in less than 6 decades. Now, scale that to modern systems. A Boeing 747 jumbo jet contains approximately 4.5 million parts, including fasteners. Here's what most people miss. This isn't just about having more components, it's about probability. If each part has a 99.99% reliability rate, which sounds incredible, a system with 4.5 million parts faces thousands of potential failure points. The math doesn't care about your confidence, it cares about combinations. Every added component creates new failure modes, new interactions, new vulnerabilities that didn't exist in simpler systems. You're not just building bigger machines, you're building probability fields where failure becomes statistically inevitable unless you engineer against it. This is why reliability engineering emerged, because complexity made intuition obsolete. So what is reliability? Not the casual definition, the engineering definition. Reliability, designated by the symbol R, is the probability that an item will perform its required function under given conditions for a stated time interval. Break that down. 3 pillars hold up every reliability calculation. Pillar 1, required function. Not what the system can do, what it must do. A landing gear must deploy. A brake must stop. A valve must seal. Failure means the required function doesn't happen. Pillar 2, given conditions. Reliability isn't abstract, it's conditional. A pump designed for 20 degrees Celsius fails at 80 degrees Celsius? That's not unreliable design, that's operating outside given conditions. Engineers must specify the environment, load, stress, and operational context. Pillar 3, stated time interval. Reliability decays with time. A component might be 99.9% reliable for 1,000 hours and 60% reliable for 10,000 hours. Time isn't a minor detail, it's the dimension where probability unfolds. Put these together and you get a probability framework, not a guarantee, not a feeling, a calculated likelihood that integrates function, conditions, and time. This precision matters because when you say a system is reliable, you're making a mathematical claim that can be tested, verified, and held accountable. But reliability doesn't operate alone. Engineers use a four-part framework called RAMS. R, reliability, the probability of required function over time. We've covered this. A, availability, the proportion of time a system is operational when needed. A system can be reliable but unavailable if it's constantly down for maintenance. Availability asks, when I need this system, will it be ready? Maintainability, the probability that maintenance can restore a failed system to operational state within a specified time interval. High maintainability means quick repairs. Low maintainability means extended downtime even for minor failures. Safety, the probability that the system will not cause harm to people, property, or environment during operation or failure. Safety isn't about whether something fails, it's about what happens when it does. Here's the connection. These four characteristics interact. A highly reliable system with low maintainability still suffers poor availability. A highly available system with low safety creates catastrophic risk. You cannot optimize one dimension while ignoring the others. Real engineering requires systems thinking. RAMS forces you to see the whole machine, not just its parts. Not all failures are equal. Engineers classify them into two critical categories. Category 1, safety failures. These failures have adverse effects on human health, property, or equipment. Consequences include injury to operators, damage to surrounding infrastructure, and, in extreme cases, death. When a brake system fails and causes a collision, safety failure. When a pressure vessel ruptures and injures workers, safety failure. When a control system malfunction triggers chemical release, safety failure. These failures carry legal and regulatory consequences. Standards like MIL STD 882 exist specifically to force engineers to identify hazards, mitigate risks, and verify solutions. Because safety failures aren't just technical problems, they're ethical violations. The engineering responsibility here is absolute. You eliminate hazards where possible. Where elimination is impossible, you minimize risk to the lowest achievable level. No shortcuts, no acceptable casualties. Category 2, operational failures. These prevent mission completion without safety consequences. An engine quits mid-flight but backup systems engage safely? Operational failure. A server crashes but no data is lost? Operational failure. The impact here is economic. Lost revenue, extended downtime, mission abortion. Expensive, yes. Deadly, no. But here's what matters. Even operational failures demand rigorous engineering because lost missions accumulate costs, erode trust, and eventually destroy market position. Prevention strategies differ between categories. Safety failures require redundancy, fail-safe mechanisms, and protective barriers. Operational failures require reliability optimization, predictive maintenance, and graceful degradation. You must know which type you're preventing. The engineering approach isn't interchangeable. Let's be direct. Reliability isn't a performance metric, it's a moral obligation. When you design a component, you're not creating a part, you're creating consequences. If that component fails in a hospital ventilator, someone dies. If it fails in an aircraft hydraulic system, hundreds die. If it fails in a nuclear cooling system, thousands die. You don't get to claim ignorance. You don't get to say that's quality's job or that's manufacturing's problem. The engineer who specifies the design owns the failure modes. This is why systems thinking isn't optional. A component-level perspective sees isolated parts meeting isolated specifications. A systems-level perspective sees interactions, dependencies, and failure cascades. When you evaluate reliability, you must ask what happens when this fails, not if, when. Because given enough time and enough units, every component fails. Your job is to ensure that when failure occurs, it's controlled, predictable, and mitigated. That requires understanding RAMS as an integrated framework. That requires classifying failures by consequence. That requires accepting professional accountability. The public trusts that bridges won't collapse, that aircraft won't fall from the sky, that medical devices won't malfunction during surgery. That trust rests on your calculations, your testing, and your integrity. You are not building products, you are building margins of safety between normal operation and catastrophic failure. The width of that margin is determined by how seriously you take reliability engineering. Now connect the blocks. Reliability affects availability. A component with 90% reliability but 10-minute repair time has different availability than one with 95% reliability and 2-hour repair time. You must calculate the combined effect. Maintainability impacts safety. A system requiring 8-hour repairs creates extended exposure windows. During those windows, redundancy is compromised. Safety margins shrink. What was safe becomes vulnerable. Safety failures demand different engineering strategies than operational failures, but both require systems-level thinking because failures don't respect component boundaries. In a 4.5 million part aircraft, a minor operational failure in one system can trigger safety failures in dependent systems. The engine sensor that fails operationally, it feeds data to flight control systems. Now you have safety exposure. This is why RAMS exists as a unified framework. Real systems don't have reliability without availability. They don't have safety without maintainability. Every characteristic influences every other. Engineers must think in networks, not nodes. Optimize for system performance, not component performance. Design for graceful degradation when subsystems fail. Trade-offs are inevitable. Higher reliability often means higher cost. Improved maintainability may reduce performance. Your job is to find the optimal balance for the mission requirements and consequence profile. But that balance must never compromise safety, ever. Economic optimization has limits. Those limits are defined by human life. Here's the final truth. You chose engineering because you wanted to build things that matter. That means accepting that what you build can fail, and when it fails, consequences follow. Reliability engineering gives you the tools to minimize failure probability. RAMS gives you the framework to manage system-level performance. Failure classification gives you the lens to prioritize consequences. But the responsibility? That's yours. The calculations you run, the tests you specify, the margins you design, those decisions create the boundary between safe operation and catastrophic failure. The public doesn't see your work. They don't see the failure modes you prevented, the redundancy you added, the safety factors you specified. They only see the systems that work. Until they don't. And then they see everything. Your professional reputation, your company's survival, and in many cases human lives depend on you treating reliability not as a checkbox, but as a core engineering discipline. This isn't pressure, it's reality. Welcome to what it means to be a professional engineer. If you're serious about engineering thinking, subscribe. We are building a library of concepts that actually matter. See you in the next one.